In lecture 10, we're going to be discussing homotopy of paths. And then later on, at some point, we'll talk about homotopy of topological spaces. Basically, the idea of a homotopy means to change. It means to change one object into another through a continuous process. And we'll define rigorously what that means. That's not the same thing as a homeomorphism. It's going to make sense later on, because sometimes you can have two different objects that are not homeomorphic, but there's going to be a homotopy between them. So let's not worry about it right now, and let's just make the definitions. So let's begin with what is known as a path. And I should say that this concludes set topology. Now we move to the fundamental group. It's going to take us several classes to introduce the fundamental group, various properties, then how to compute it, and all that stuff. And then once we are well familiar with the fundamental group, we will then move to the third part of the course, where we use the fundamental group to help us solve various problems in topology. So the main idea for the next several lectures, really I would say the next third of the semester, is to introduce the fundamental group and all of its properties and calculations and all that stuff. And that definitely takes some time to introduce, but it's a very important object in topology, so we will definitely be rewarded for all of the hard work we put in. So no more point set topology. So if you have not enjoyed point set topology, we get to move on to something new. It's going to feel different. Maybe you'll like it more. Though I would argue that the point set topology that we've been doing was not too bad. It was somewhat interesting. But if we kept on going, it would eventually get to the point where it's not interesting anymore. Okay, so let's maybe recall what is a path-connected space. Take this definition. You say that X is path-connected, if and only if, for any 2 points, P and Q in X, we can find a continuous function from 0, 1 into X, such that f of 0 is P and f of 1 is Q. That's what we call path connected. The reason why it's called like this is because the picture is, this is our space X, we have a point P, we have a point Q, and then we have the interval from 0 to 1, and we're saying there's a continuous map that takes this interval and it maps it continuously into the space. So this interval will therefore be mapped somewhere between those two, and so you end up getting some kind of path. Maybe it intersects itself, it does not matter, but you end up getting some kind of path that's going to move from P to Q. So f of 0, this is where you start at P, and f at 1, that's the endpoint that ends up in Q, and then you have some kind of path between those 2 points. You can of course have a path going from 0 to any other number, and like in general you can have a path from A to B, but you can always rescale. So like if you go from 0 to 2, you can go from 0 to 1, and then the time parameter, you would just replace it by let's say t over 2. So if the time parameter moves from 0 to 2, then by replacing t by t over 2, you're going to have time move from 0 to 1. So actually, I should say it's really 2t from 0 to 1. So if time moves from 0 to 2, if that's the time parameter, then 2t will trace out the same amount of time, like twice as fast, but this time from 0 to 1. So you think of this interval as sort of representing time. That's the intuition here. This is what happens at time 0, this is what happens at time 1, and you can always rescale, so it goes from 0 to 1 to make it as convenient as possible. And we often use the notation, we just call this I for the unit interval. So to save space, we'll keep on referring it, we'll refer to this interval as I in this lecture and probably a few other lectures. So that's what is known as a path-connected space. And this is known as a path. So let's actually single out this definition. Let's just add this. So a path from P to Q in X is a function. And it's a continuous function, of course. How about we make this convention that from now on we stop saying continuous. So whenever we say function or whenever we say map, we always understand that we're talking about something that's continuous, right? That's because we're doing topology, and so we only work with continuous maps. So we have a function from the interval from 0 to 1 into X, where f of 0 is P and f of 1 is Q. So that's what we mean by a path. By the way, P and Q could be the exact same point. So if P and Q are the exact same point, then a path would be like a closed path that returns back to where you start. So that's perfectly fine. You can talk about a path from a point to itself, in which case you have a closed path. That's what we call a closed path. Okay, so that's the definition of a path. So now I want to introduce something called the constant path. So here's definition. The constant path at P, so this is in some space X. There's always some topological space in which we're working in. Let's define it as EP is the function that maps. So a path in X is always a mapping from the unit interval into X. And you have to give it the formula. So the formula here is that it's always equal to P. That's why it's called the constant path. So intuitively, this is the path that just stays at P and it never moves. So that's the simple idea. That's what we call the constant path. So not very interesting, but you're going to see the reason why we are introducing it. And there's also something called the reverse path. So let's take this down. So here's a definition. So if f is a path from P to Q, the reverse path from Q to P, and the notation that we use is we can put a bar over it, the reverse path. So f is a function from the unit interval into X, and it maps 0 to P, and it maps 1 to Q, and the reverse path goes in the opposite way. It's also a path, so by definition, a path is always a mapping from the unit interval into your space, but this one goes the other way. This one will go from Q to P, so it goes in the opposite way, and you just make time flow backwards. That's basically what you do. So it is defined by, so f bar of t, you make time go backwards. Now you cannot write negative t. That would not make sense, because the original path, you see this is the original path, it's only defined when the time parameter is between 0 and 1. So that's not going to make sense. But what you could do is you can write 1 minus t. And now notice what happens if you set t is equal to 0, then you have f of 1. And f of 1 is q. So f bar at 0 is equal to f of 1, so that's q. And if you set t is equal to 1, then f bar of 1 would be equal to f of 1 minus 1, so that's f of 0, and f of 0 is p. So this is the path that, it's the exact same path, but it just goes in the opposite way. So if this is the path that goes from P to Q, and it has this orientation, then the reverse path, it's the exact same path, but it has an opposite orientation. It goes from Q to P. So that's what this is. So you can always flow backwards. So we call that the reverse path. So now we're going to define what is known as a path homotopy. Path homotopy. So before we give the definition, I want to give a little bit of an intuition. So let's say you have 2 points in your space, and you have some kind of path, let's call it F, and then you have another kind of path called G. So a path homotopy is a continuous, you can say, deformation from one path to another path. So in the picture, what this would be is, you can imagine that you're sort of bending this, you're kind of bending it. It's kind of like a topological space. You're sort of bending this to fit in there. And I know what you're thinking. You're probably thinking to yourself that these two paths are, so these two curves are homeomorphic as topological spaces. But you have to really understand, a path is not really a path is not really a topological space. A path is a function from the interval into a topological space. A topological space is just X. So we have to use slightly different vocabulary. We talk about two spaces being homeomorphic. But when we're talking about paths, paths are technically maps into a space. And so we have to use different vocabulary for something like that. And the idea is, you can continuously deform one path by bending it in some kind of way so that it resembles another path. Now, what you need to be careful about is if your space has some kind of hole in it. So let's draw this picture. So let's say this is your space X, and it has a hole in it. So this is your space, and the hole is not part of the space. And then you have 2 points, P and Q, and then you have a path. One of these paths is F, and you have another path over here. Maybe it does something like this, and that's G. You would say, so in this picture, you would say, so here, F and G are not homotopic. So that's the vocabulary that we use. Because in this particular picture, it is not possible to deform this path into that path, because that will require you to pass through that hole. But that hole is not part of your topological space. So sometimes paths are going to be homotopic, and sometimes they will not. And it essentially has to do with whether or not there's a hole in your space. So here is the rigorous definition of how you do this. Here's the definition. So we're going to fix 2 points, P and Q, in X. And these 2 points, they could be the same. They could be the same, but they could be different. But we'll just allow, for now, the possibility that they could be different. And later on, we'll specialize when they're the exact same point, and then you're going to be having closed paths. But for now, let's just allow the possibility that they're different. So you have 2 points in X, and F and G are paths from P to Q. So F is a mapping from the unit interval into X, and G is a mapping from the unit interval into X. And at time 0, they're both equal to P, and at time 1, F and G are both equal to Q. So these are continuous maps. So you have 2 of them. So we say F is homotopic. So actually, I think it probably makes sense to say path homotopic. Later on, we will discuss what is known as space homotopic. You can talk about spaces being homotopic, but for now we're talking about paths being homotopic. So F is path homotopic to G if and only if there exists a map. And the name of this map, this is called the homotopy map. So the homotopy map is the map that makes these, that deforms one path into the other path. Let's call it h, and it goes from I times I into x. So I'm going to do something that will make it a little bit easier to have some intuition. So let's call time. So let's think of the input variable as time. You kind of think of this as time. So f of t gives you something in x. And with a homotopy, notice you have two i's, right? You have a product of two i's. You're going to think of this as time, and you're going to think of this as s. So this is going to be time, and this is going to be, I'm going to call this interpolation. And I'm going to draw a picture here. So the picture is, here's your point P, here's your point Q, this is F, this is going to be G, and the way you get F is when you set S is equal to 0. And the way you get G is when you set S is equal to 1. If you set S to be any number between 0 and 1, you're interpolating. So interpolation means to fill in the gap. You are interpolating the space that is in between them. So you can have, let's say, you have something going like this. So maybe that is what happens when S is equal to, let's say, 1/4. And then here you have something that goes like that. That is what happens when S is equal to 1/2. And so when you flow, this is the interpolation parameter. When you flow the interpolation variable from 0 to 1, you begin with the original path, and then you continuously deform it into the second path, and it continuously fills in the space in between them. So that's the picture that you want to have. But formally speaking, F is path homotopic to G if you can find a mapping from I cross I into X, so that this is a continuous mapping, so that H of X comma 0 is equal to F of T, and H of T comma 1 is equal to G of T. So you see what's going on. When you set the interpolation parameter to be 0, H of T is the same thing as F of T. That gives you the original path. When you set the interpolation parameter to be equal to 1, H of T1 will give you the second path. And then when you make S range from 0 to 1, you're just getting the intermediate paths in between them that fill anything in. Now, if you're not familiar with this word interpolation, sometimes what people mean to say is, if you have like a bunch of points, let's say if you have like a bunch of points, and there's like a lot of things that are missing, sometimes when people say to interpolate the points, means to sort of fill it in with some kind of curve that goes in between them. So that's what the word interpolate means. So what I'm saying here is, there's a lot of space in between them, and you're just sort of filling them in. So this is the way you want to think about this. So that's what is known as a path homotopy. And I guess I should say one more thing. I forgot to say this, that while you're doing this homotopy, all of these paths, these paths in blue that are in between, they always go from they always go from P to Q. So these are sort of the two fixed points that never change. And maybe we can add and H of, let's say, 0 comma S is always equal to P, and H of 1 comma S is always equal to Q. So you're not going to have a situation where one of these will go something like that. That these are the two fixed points where you start and when you finish, and that all of these intermediate paths that interpolate between F and G also always start at P and finish at Q. So that's the requirement. That you see, if you set S to be some number between 0 and 1, let's say S is equal to 1/2, then when you evaluate T from 0 to 1, you will get some kind of intermediate path, and you're saying that intermediate path, when evaluated at 0, should begin at P, and it should finish at Q also. So that's what we mean by a path homotopy between them. So that's the definition of a path homotopy. And let me remove this. And since in topology, we do not care how we bend, twist, form things, it is reasonable to define paths which are homotopic as the same. So let's introduce some notation. So if f and g are paths from P to Q in some space X, we use the notation F. So it's very similar notation that we've been using before for a homeomorphism, but we're using sort of similar notation because of overloading. We kind of use this notation quite a lot in mathematics. This is sort of like the congruent notation to mean that F is homotopic, and let's just emphasize path homotopic to G. And so here's a proposition. Path homotopy is an equivalence relation. So what does that mean? It means three things. It means F, any path, is homotopic to itself. The second one says that if F is homotopic with G, then G is homotopic with F. And the third one says that if F is path homotopic with G, and G is path homotopic with H, then F is path homotopic with H. So that's what we call an equivalence relation. We want to treat homotopic paths as being the same because you can deform one into the other. And it's nice to see that this notion of a path homotopy is an equivalence relation. This is quite similar to when we talked about equivalence relations before. When you want to treat things as similar, even though they might be a little bit different, you want to have an equivalence relation. So the fact that path homotopy is an equivalence relation is an indication that we are on the right path, to use a pun, with this idea of treating paths as being the same. So most of these are actually very easy to prove. And instead of proving all three of them, let's just prove one of them. So let us prove 3. And as an exercise, you can prove this one, and you can prove that one. It's not difficult to do. You can find it done in Moncrief if you're not sure how to do it, but I think you'll be able to do it. It's important to do these easy things because whenever you're learning something new, you really have to understand the definitions. As we all know, math is about the definitions. It can be argued the definitions are more important than the theorems. If you do not know the definitions, you're not really able to do anything. So a lot of the times, sometimes when you're trying to prove something, it's not necessarily very hard. It's just you're misunderstanding the definition. So that's why the definitions are so important. So even though these exercises might seem very silly, they're very good at practicing these definitions. So let's do part 3. So let's see how you do part 3. So here's what I want to say, that suppose F, G, and H are paths from P to Q. They all have to go from P to Q. They all have to go from one point to another point. Because if G goes, like, you would not say, like, I want to kind of maybe address this. Let's say you have 2 points over here, and you have 2 points over there. So let's say this is F, and let's say this is G. When you look at a picture like this, it can be argued that these are homotopic because you can kind of slide this one in place, and then you kind of get the 2 paths. So I understand that from the picture, but the definition of a path homotopy, this is the way the definition is set up. In the definition of the path homotopy, paths are required to start and end at the same point. So even in the picture that you see over there, you can see that you can continuously deform F into G. You would not say that they're path homotopic because the definition of a path homotopy requires that the paths start and end at the same point. So whenever we write F homotopic with G, it is automatically assumed that they start and end at the same point. So, okay. So since F is homotopic with G, there is, okay, so maybe I should just add this. So it's not required, but think just to recall, F goes from I to X, G is a mapping from I to X, H is a mapping from I to X, F of 0 is equal to G of 0 is equal to H of 0, and they're all equal to the initial point P, and F of 1 is equal to G of 1 is equal to H of 1, and all three of them are equal to the terminal point Q. So not required, but I just want to emphasize that so we do not forget. And since F and G are homotopic, there is, by definition of path homotopy, there is a homotopy. Now, I cannot call it H because I'm already using H, so maybe I'll call it capital H. So let's call it capital H, and let's call it capital H1. So this is a path homotopy that goes, so the definition of a path homotopy is this. I think of the second one as interpolation, and I think of the first one as time. There's a path homotopy H1 so that the following properties are satisfied. H1 of T0 gives us the first path, so that's f of t. H1 of T1 gives us the second path, that's g of t. Then we have the H1, so when t comma s is always equal to p, so that means all of the intermediate paths all start at p, and H1 of 1s is equal to q. So that is the definition of a path homotopy. There's a mapping, right? There's a mapping from that square into x. Maybe a picture would be helpful. So here's like a picture. So think of this as the t-axis, and think of this as the s and the s-axis. So this is like your square, and this is your space x. This is p, this is q. So the picture is that this lower edge, right, this entire lower edge, this is what happens when s is equal to 0. So when s is equal to 0, that entire lower edge gets mapped to f, that's f. So that will give you f. So that's going to give you f. So that's going to get mapped somewhere, so it gets mapped to f. Then this upper edge, so this entire upper edge, so this is what happens when you set s is equal to 1, then you get g. So as you move along this upper edge, you're getting g. Okay? And the left edge, it's always equal to p. It's constant. It's always equal to p. So this entire left edge right over here and this entire right edge, they get mapped to p and they get to q and they never move. So this is the idea of what's happening. And this mapping is what you call H1. It sort of maps this square into a picture like this, and all of the stuff in the middle is the interpolation that takes place between the two paths. So that's like a helpful picture to have in mind. And you can, of course, look in the Moncrief's book. He has a lot of nice pictures like that. Now, we also say that G is path homotopic with H. And we're going to say that since G is path homotopic to H, there is, by definition, a mapping, let's call it H2, that's called a homotopy mapping, that takes us from I to I into X, and it satisfies the properties that H2 of T0 is equal to G of T, H2 of T1 is equal to H of T, H1 of 0s is equal to P, H2 of 0s is equal to P, and H2 of 1s is equal to Q. So these properties are now satisfied. So now construct the following mapping. So the idea of this mapping is, so what's the idea of this mapping? So the idea of this mapping is you want to get a homotopy that will take you from F to H. So you first deform F to G, and then you deform G to H. So you have to somehow combine these two homotopies. So you're going to create a new homotopy. This is the one you're claiming exists, right? Because when you're saying that F is homotopic with H, what you're basically saying is there exists a homotopy that will transform F into H. So you basically have to construct it. That's the claim. This is the given, and that's the claim. So we're going to construct the following mapping. Let's call it H3, and it's a mapping from I times I into X. And it's going to be defined as follows. H3 of T comma S is equal to, so here's the way we're going to do it. We have to somehow use the two previous ones from before, and this is the way we do it. We're going to write H1 of T comma 2S, and this is if S is between 0 and 1/2. Okay, so let me tell you basically the idea of what we're happening. So we have the time parameter and we have the interpolation parameter. The interpolation parameter is supposed to interpolate from 0 to 1. Now, the idea is we go from 0 to 1/2. We go halfway in. So we have two homotopies. We have H1 and we have H2. So the idea is we're going to make this interpolation parameter move twice as fast. We're going to make S go from 0 to 1/2, but we make it move twice as fast. And by doing that, what happens, we end up with H1 of T comma 1. You see, when 2S, so if you have 2S and S is equal to 1/2, you end up at 1. And then you have G of T. Okay? And then afterwards, you continue it with the other homotopy. So you write H2 of T comma, and this is if S goes from 1/2 to 1. Now, the problem is that in the original homotopy, you see it starts at 0 and it goes to 1. Now, if S is equal to 1/2, the correct way to write it is you have to write this as 2S minus 1. Because if S is 1/2, if S is 1/2, then this is 1 minus 1, so that's 0. So you're getting this, you're getting H2 of T0, which is G of T. And if S is equal to 1, then you get 2S, which is 2, minus 1, that's 1, and you're getting H2 of T1, which is H of T. So this is what you get. Okay, so for the moment, so we need to verify that H3 is continuous. I mean, if you just make up a function, you have to know that it's a continuous function. There is a little bit of fear here that because you have something that's defined in a piecewise manner, maybe it stops being continuous. So we actually have to check that it's a continuous function. So what I want to do is I want to accept for the time being that the function is continuous, and then we'll return back to that. So let us accept for now continuity and see if H3 is a homotopy from F to H. And then because that's what we want to show, right? We want to show that F and G are path homotopic. So how does one do that? Well, let's see. What is H3 of T comma 0? Well, that would be equal to, since S is 0, that would be equal to H1 of T comma 0, and H1 of T comma 0, that was F of T. That is something we've said before, right? We said it all the way up here. And if you do H3 of T comma 1, then that would be equal to H1. I'm sorry, that would be equal to H2 of T comma 1, and that is equal to H of T. Right? That would be equal to, this is what happens when we set S is equal to 1, and then it's 2S minus 1, so it's H2 of T comma 1, which is H of T. Then you have to see what happens at the endpoints. So H3, when time is 0 at S, what is that equal to? Well, you can see that regardless of what interval S is located, whether S is here or whether S is here, both of these homotopies at 0 are all equal to P. So that's equal to P, and for the same reason, this one will be equal to Q. So we have constructed a homotopy from from F to H. And that would complete the proof. The one part that we need to verify is that the function is continuous. So usually this is the most boring part of arguments, and sometimes it's acceptable to just assert things that assert that things are continuous without checking them, because usually when you put things together, they're going to be continuous unless you do something really wrong. If you're on the right track, it's almost always going to be continuous. But just to carefully verify how you do it, you have two pieces. So we know that, so what do we know? We know that H1 of t comma s is a continuous mapping. But here we have 2s. So why is that continuous? So it's continuous because of a composition. Because you're basically mapping ts into t comma 2s, and then you're following through by H1. So this is the mapping from I times I into I times I, where the second coordinate is being doubled. This is a continuous mapping. I'm sure we can check that, right? This is just a linear mapping on the second coordinate. And then this is what we're calling H1. So we're doing a composition. We're mapping this to this, and then we're applying H1 to that. And the composition of continuous maps is continuous. So this will mean that this upper function is continuous, and this lower function is continuous. Now, this is a closed interval, and that is a closed interval. And you had a problem on the homework that said that if a space is a union of two closed sets, and the function and the functions when restricted to those two closed sets are continuous, then the function on the entire space is continuous provided they agree on their overlap. So you had that probably in like homework number 3 or something. You can look at that. So it's important that you have closed sets. So these are closed sets. The overlap occurs at 1/2. Now you can see that when s is equal to 1/2, this is H1 of T1, and H1, you see, H1 of T1 is G of T. That is G of T. Now, when s is equal to 1/2, this is H2 of T0, and H2 of T0 is G of T. So on the overlap, where s is equal to 1/2, this one and this one, they agree, and they give you the same function. So by the gluing theorem, or something like this is when you can glue two continuous maps together, you can conclude from here that this function is therefore continuous. Okay, so that's the way that it works. So that's a very long proof for something very simple, but I wanted to be extra careful because we are learning this for our very first time, and wanted to carefully write it out. And you can check something similar for these two. Okay, so we know that homotopy is an equivalence relation. Now here's an interesting proposition. This is actually quite easy to prove. Proposition: let C in Rn be a convex set. So convex, to just quickly recall, something that looks like this. Let's say that if you have any 2 points, the line between them always stays in the space. That's what it means to be convex. Let it be a convex set, and P and Q be any 2 points in C. Then if F and G are paths from P to Q, then F is homotopic with G. That should make sense, right? That should make sense because this is your convex set, and if you have 2 points, this is sort of the path, one path, and this is another path, and the entire idea is basically based on the fact that if you were to connect any 2 points on the path by a straight line, that straight line falls within your convex set. So that's why convexity here makes everything simpler. So here is how we prove it. Proof is fortunately very simple proof. We will construct a straight line interpolation. So here's how we do it. So we're going to have a homotopy. It's going to take us from I times I into our convex set. So think of this as the time parameter, think of this as the interpolation parameter. And the way we do it is h of t comma s, it's going to be equal to f of t times 1 minus s plus g of t times s. Okay, that's what this means. So just so we understand, this is a scalar, this is a scalar, this is a vector, and this is a vector. So I guess maybe we usually put the scalar in front, but let's not obsess about that, because f, this f, it is a path in the convex set, and a convex set, it's a subset of Rn, so it consists of vectors. So what we're saying is, the way this is being constructed is, you apply on t, you apply f of t, that gives you a vector, you multiply it by 1 minus s, and then you do the same thing with g of t, and then you multiply it by s, and then you add those two vectors together, and whatever that is, that's going to be something in C. Now, why does this work? So let's just, so this works, so this works. So maybe just to recall this, the straight line segment, from P to Q is, it's P, so it's like SP plus 1 minus S. Maybe we write it like this. It's 1 minus SP plus SQ. So if you set S is equal to 0, you get P, that's your vector, which you're going to draw as a point. And if you set S is equal to 1, this goes away, that's going to give you Q. You're going to draw that as a point and not as a vector. And now if you let S flow from 0 to 1, that's just going to give you a straight line that's going to move like that. So that's the straight line segment from P to Q. So the idea here is quite simple. The idea is that as you move along the F paths, so as you flow along this path, F of t is your position after t seconds, and G of t, that's your position after g seconds. And what you're doing is you're just creating the line in between them. So that's why we call it the straight line interpolation, which we can use to create our homotopy. The important thing is this ends up in our space. It ends up in our space precisely because it's a convex set. This is a point in the convex set, this is a point in the convex set, and that's the straight line segment between them. Now, one does have to check that this is indeed a continuous map, but I think that's believable, right? F is continuous, G is continuous, and we're just putting scalars in front and we're combining them together. So, of course, it requires a check, but if we check every single little thing, these classes would be like 10 hours long. These classes are already long as it is. So that's the way you do it. Now, I want to give you a warning. A subset of Rn does not need to be convex for this to be true. So for example, I think we can agree by looking at this picture that this hourglass has the exact same property. That if you have F, and if you have, let's say, G going like this or something, that it's still true that, so let's say G was to go something, well, I'm not sure. Let's say G was to go something like this. Then, well, let's say F, I'm not sure, goes like this, and G goes like that or something. Then it's conceivable that like the straight line on one and the other, I'm actually drawing it to the same point. So I guess on G, well, I'm drawing it in a bad way, but maybe I should exaggerate it a little bit more. Let's say we have something like, I'm not sure, like this or something. So that's certainly not convex. And then you have F, this is F, and then you have another path. So you have another path or something that goes like this. Then it's conceivable that if you pick a point on one path, see, this is like a point on one path, and you pick the point on the other path, that the straight line segment is not part of your space anymore. So the straight line homotopy would not be valid here because you're leaving your space. But despite that, we can see that the space is sort of filled in. There's no holes in the middle. So nonetheless, it should still be true that any two paths that begin and end at the same point should nonetheless be homotopic. But that requires a definition of what it means not to have holes. And that's something we're going to eventually work up to. So for the time being, we're just doing it for convex sets because they're very easy to define, and it does not take a lot of work. Defining what it means not to have holes, that will actually take more work. So now I want to define something called the multiplication of paths. Multiplication of paths. And I like to also call this juxtaposition of paths. That the word juxtaposition means to put two things next to each other. So the situation here is going to be that, suppose f is a path from, let's say, from P0 to P1 in X, and G is a path from P1 to P2 in X. So notice that they are from different points. But if you draw a picture, this should be clear. We have P0, we have P1, and P1, and we have P2. The idea here is this is F, and this is G. And juxtaposition of paths, Moncrief calls it multiplication of paths, but I'll call it juxtaposition. So juxtaposition of paths is exactly what you think it means. You flow along one path, and then you flow along the other path. And that gives you a path from P0 to P2. So we define an operation, let's call it star, so Moncrief calls it multiplication, but I want to call it juxtaposition. Juxtaposition that does this. It takes F star G and defines a new path. So what is a new path from P0 to P2? So what is a path? So F star G has to be a mapping from the unit interval into your space X, because that's what a path is. By definition, a path is a mapping from the unit interval into your space. And you have to say what it does to the time parameter. Well, there's two paths here. The idea is, and this is very similar to what we did in the homotopy example, is we're going to speed up time twice as fast, and we're going to flow along this one twice as fast, and then we're going to flow twice along this one twice as fast. And then we kind of have these two paths. So it's going to be f of 2t. So f of 2t, and this is if t is between 0 and a half. And then it's going to be g of 2t minus 1 if t is between 1/2 and 1. And this is an operation on paths where you're combining two paths together to create a new path through this juxtaposition process. Okay, so now you technically have to check that this is a continuous mapping, otherwise it's not a path. But I mean, it's the same reasoning as before. Now, I want you to notice a few things. What happens when time is equal to 0? Then that's f of 0. F of 0 starts at P0, so it is a path that begins at f0. Now, if t is equal to 1, then this is g of 2 minus 1, g of 1. So that's the endpoint of g. But as you can see, g is a path from P1 to P2. So the endpoint is going to be on P2. So you have constructed a direct path from P0 to P2. So we have that. And the reason why this is continuous, the main thing you have to check is what happens on the overlap. If you said t is equal to 1/2, do both of these formulas give you the same thing? So this is f of 1, that's the terminal point, and this is g of 0, that's the beginning point of g. And you can see that f, the terminal point of f is P1, and the initial point of g is P1. So they agree. Okay, so this is what we have. So that's the path. So maybe we make a warning here. Warning. Juxtaposition. So f star g is only defined if f of 1 is equal to g of 0. Right. So this is the end, and that's the start. The end of f has to agree with the start of G. Otherwise, you're not able to put them right next to each other and get a path out of that. Okay, so it's only defined. So F star G may be defined while G star F might not. Okay, so this operation, so star, is not commutative. It's not a commutative operation because the order here matters. This should perhaps remind you of matrix multiplication, that if you take two matrices and you multiply them, you get an answer. But if you interchange the order of the matrices, matrix multiplication might not even be defined. So you're not even able to get an answer. Okay, so this is what we call juxtaposition. And now I want to write down, I want to say this. So this is going to be an interesting result. So proposition juxtaposition is well defined with respect to path homotopy. In other words, so more precisely, if F1 is homotopic with F2, and this is, let's say, a path from, let's say, from P0 to P1, and G1 is path homotopic with G2, and this is a path from P1 to P2, then F1 juxtaposed G1 is going to be path homotopic with F2 juxtaposed G2. That's the idea. So well defined means the answer does not change. So well defined. So basically, what well defined means is that even though you can make choices, the calculation is the same. So you get the same answer. Now, when we say you get the same answer, what we mean the same with respect to path homotopy. So if you take two different paths that are the same, so they're the same in the homotopic sense, and then you take two other different paths, but they're the same in the homotopic sense, then if you do this juxtaposition and you do that juxtaposition, you will, of course, get different answers. But when you look at it from the point of view of homotopy, the answers come out to be the same thing. So that's what we mean well defined. Well defined means there is no ambiguity about what you get. If it was the issue, yeah. So this will be important when we end up defining the fundamental group. So you'll see how this gets used later on. So this is a proposition, and it's not difficult to prove. If you draw a picture, I think the picture makes it very, very clear. So this is like F1, and this is F2, and this is G1, and this is G2, and you can take a homotopy from F1 to F2 and a homotopy from G1 to G2. So if there's a homotopy, then you can kind of maybe combine the two homotopies together, and when you do the entire juxtaposition like this, then you can hope this one to the other one. So it's believable when you draw pictures, and you can write your own formal proof. It's similar to the other ones that we've done before, and I think it therefore would be a good homework exercise. It's not difficult at all, but it's a good practice in the definitions. And you can, of course, find it done in Moncrief, though I would suggest to try doing it yourself. Okay, now I want to get to another proposition. Here's another proposition. So these are properties of juxtaposition. So here are the various properties that we have. So the first property, this is called the identity property. This is called identity. So it says that if F is a path from, let's say, P0 to P1, then if you take the constant path and you juxtapose it with f, that's going to be homotopic with f. And if you take f and you juxtapose it with the constant map on the right, that's going to be homotopic with f. So notice the one on the left and on the right, they have to be different, because otherwise juxtaposition will not be defined. So the picture makes this very clear. P0, P1, and we have our path f. Well, what is the constant path? The constant path is the path that sits at P0. So we have our sort of constant path EP0 over here. So if we move along the constant path, which just means you stay there, and then you move along f, that would be path homotopic to the f that you started with. Though the formulas for these two would be different. I'm not saying this is equal to that. If you actually write out the formula for this path, it's not equal to f, but it will be path homotopic to that. And here it's on the other side. So here it would be on the other side. Here you're going from P0 to P1, and this is f. You cannot juxtapose this with E of P0 because it's not the terminal point. It actually has to be on the other side. So when you do that, it's homotopic. So what it shows is that the constant path that does not move is in some sense like an identity element. Now, as you can see, when you do juxtaposition, you do get a different path. However, if you look at everything in terms of homotopy, right, if you treat things that are homotopic as the same, if you identify them as being the same, then you are getting the same answer. So f, you start with the same path and you finish with the same path because they're homotopic, like up to homotopy, you're getting the same answer. So it somewhat plays a role of an identity element. Now, the other thing I want to mention, so you have an identity, and then you can talk about this thing called the inverse. So this is property 2. This is called the inverse. So if f is a path from P0 to P1, then if you do f juxtapose the reverse path, so this is the reverse path, then this is going to be homotopic. So you're going from P0 to P1, and then you're going from P1 back to E0. So this is going to be the constant map at E0, and if you do the reverse path first, and then you follow it by f, that's going to be homotopic to E of P1. So you have these two. And I'm going to be lazy again, because if I start proving every single one of these, this lecture will get fairly long. So this is going to be an exercise on the homework. This is, again, not difficult to prove. It's very similar to the other ones. It's done in Moncrief. If you're confused about something, you should at least write out a part of the proof. And then if you're not sure how to proceed further, you can just see what Moncrief does. And then the next one is actually fairly difficult. It's a computation. So that's the one we're going to talk about in more detail. So this is going to be the next one. So this next one, this is the third property. This is the one we're actually going to prove. This is the most difficult one, and this is called the associative property. So here's how it goes. It says that if f is a path from P0 to P1, G is a path from P1 to P2, and H is a path from P2 to P3, then the associative property says that you can do F juxtapose G, and that will give you a direct path from P0 to P2, but then H goes from P2 to P3. So then you can juxtapose that with H. But you can also do it this way. You can do F, you can also do this. And the formula for this one and the formula for that one are going to be different. So if you actually write out the formulas are going to be different, and they will not be, so the formulas will be different, but the paths that you get will be homotopic. So in some sense, on the level of homotopy, you have an associative property. So let's discuss how to prove it. So Moncrief actually has a very nice proof of this. If you look up the proof of the associative law for path homotopies with respect to juxtaposition, other books, their proofs are more complicated. So all of these proofs are somewhat complicated because you have to somehow find the formula for this, and then take that formula and then recalculate the formula for that, and then no matter what you do, there's like a lot of computation that comes up. So it's fairly messy. So I think out of all approaches, Moncrief has the nice one, so we'll discuss the approach that he uses. So I wonder if it's his own original proof, but let's discuss the approach that he uses. So the idea that Moncrief has, so the idea is to define a triple product. Now, product means you multiply two things together, right? You combine two things together. So when you have three things, you do it two at a time. You either combine these two and then you combine that, or you combine those two and then you combine that, and then you show the order in which you do it. Does not matter how you do the bracketing. But a triple product is when you sort of combine three things simultaneously together, which is not really what a product is. But that's why I put it as a triple product in quotation marks. So the idea of Moncrief is to sort of just define this automatically. F, G, and H, triple product, and then proceed from there. So here's the way you do it. You're going to pick numbers, let's say between 0 and 1, because whenever you talk about paths, time flows from 0 to 1. So this is sort of the cutoff points. You say you're going to go from 0 to A along this one, from A to B along G, and then from B to 1 along H. So that's why you have like these cutoff points. Which one is being activated, right? You have three different functions. These are like the intervals where they're going to be activated. So this is going to be the triple product. And let's denote this by TAB. So this is not the notation that he uses, but I find it helpful. So we call it T for the triple product of these three at the same time. So this is the way you're going to define it. So this is going to be a mapping from I to X. Okay, so this is going to be a path from P0 to P2. So that's going to be a path from P0 to P3, because we're going from P0 to P1, from P1 to P2, and then from P2 to P3. So this is going to be a mapping from P0 to P3 where we kind of go F, G, and H. And these are going to be the way we're going to make time go. We're going to make time go from 0 to A along F, then from A to B along G, and then from B to 1 along H. So this is the way you're going to define it. So this is a function, so we have to say what it does at time t, and it's going to have three piecewise conditions, because you're going to activate three different functions depending on where you're located in time. So you're going to say that if, let's write it like this, so if t is between 0 and A, you're going to activate the first function, right? You're going to do f first. But the problem is, of course, you cannot just write f of t, right? You cannot just write f of t. That's going to be incorrect, because each of these functions, time goes from 0 to 1. So the idea is, by the time you reach A, time is rescaled so that this is really like f of 1. And in order to do that, this would be t over A. That would be the correct way to write it. It would be t over A. Now, these formulas can get somewhat messy. And the formulas is not what matter. It's the idea behind them that matters. So instead of writing t over A, I'm going to write this. It's f of the following. This is going to be the affine map that takes you from 0A to 0,1. That's what it is. It's the affine map. If in case you do not know what an affine map is, so an affine map, let's call it A of x. An affine map is of the form ax plus b, which I guess in a pre-calculus class one calls it linear, but it's not really linear because you're adding a constant. It's not like a linear mapping of vector spaces. I think it's more appropriately called affine. If you want to call it linear map, you can call it linear map. So this is the affine map that takes you from 0A to 0,1. So the picture would be is you have a line. This is A, this is 1. So you have a line that kind of goes like this. So then A of x, the slope of this line would be 1 over A. That would be the slope of the line. So the slope of the line is 1 over A, so it's f. So what's the affine map? It would be, ax plus b. B is 0 here, b is 0, and the slope is 1 over A. So it would be t divided by A. That's what we had before. But the formulas here do not really matter. That sort of misses the whole point. So we want to try to avoid using formulas because then it gets even messier. And then we're going to, so we're first going to activate f, then we activate g. We're going to activate g when time is between A and B. So when it's between A and B, we're going to activate this function. And here, the formula is going to be a lot more complicated because not only you have to rescale it, but you also have to shift it. So I'm just going to say that this is G, and you just have to find whatever is the affine map between A and B that takes you to 0, 1. It always has to take you from 0 to 1 because each of these path functions are defined from 0 to 1. So you always have to properly rescale everything. And then this is going to be the third one. This is if t is between b and 1. And this is going to be the affine map that will take you from b to 1 to 0, 1. So if you happen to find the formulas for these, you would have the explicit equation. So the first one is the easy one. This is just t divided by a, right? That's the easy one. But the other ones get a lot more complicated because you have a slope, you have an intercept. Let's rather not figure that out because that's sort of missing the whole point of this. And this is a path from P0 to P3 because you start at F, you finish at H. So you go from this one to this one, and this is continuous because the places where each of these, when they properly rescaled, they all finish and end at the starting and end points, so they all agree at the overlaps on the interval. So this is going to be a continuous mapping from the interval into X. So this is the way you define the triple product. Okay, so you basically have different choices how to define the triple product. You can, so you see, you're trying to define the path using all three. So you have to choose the cutoff points. You want to choose exactly when you activate each of the functions. And what Moncrief shows is, so this is what he shows. So the claim is that if you pick a different cutoff point, so if you decide to cut up the interval from 0 to 1 differently, then the path that you get, the triple product path that you get, whether you cut it up like this or whether you cut it up like that, they will be homotopic to each other in the end. And so because of that, you can then take advantage of this and prove the associative law. So let's accept this claim, right? So let's accept this claim for now, and then we'll justify the claim afterwards. I want to show you how the associative law follows from this. So from this claim, we can justify the associative law. So a computation will show, so it is at this point where a mathematician feels very bothered because no one wants to do a computation, but we'll do a part of the computation so you get to see it. And it's not difficult, it's just some tedious but straightforward stuff. So a computation will show that this product, this juxtaposition, so when you do it like this, that would be the same thing as taking the triple product that we've just defined with the following cutoff intervals. And the triple product, and this product can be, is what you get when you take the triple product with the following cutoff intervals. Okay, but these are homotopic. They're homotopic to each other. So since they're homotopic, so this is the claim. They're homotopic to each other. And since they're homotopic to each other, it means this juxtaposition and that juxtaposition are homotopic to each other, right? So that's kind of what we wanted. So there's really two things that one has to do. We still have to justify the claim, but you might be wondering, and this is what we all should be wondering, is why is this true? Like where does that come from? So I think this one I should just put on the homework and you'll do the computation. But yeah, so let's discuss why this works. So this is, as I said, this is a computation. You actually have to compute things. It's pretty boring, but I at least want to write out some steps so you get to see why this works. So maybe for simplicity, let's call this entire thing L for left. That's the piece on the left side. So let's compute the formula. So this is a path, right? That's a path. So because it's a path, it's a function of time. where time is between 0 and 1. Let's see what this is. So this is equal to, by definition, right? This is by definition. Let's write this out. So how does one do juxtaposition? The way we do juxtaposition is, so we're just calling all of this L. How does one do juxtaposition? We first move along L twice as fast, because there's two of them. We move along L twice as fast. So this is going to be L of 2t, and this is if t is between 0 and 1/2. And then, after that, we move along h. So then we do h of 2t minus 1 if t is between 1/2 and 1. So that's just the definition. So if you go back and you look at the way path juxtaposition is defined, it's just defined by moving along this one and then moving along that one, but just twice as fast. So you connect the two paths together. But then you see we have L of 2t. So then we have to find the formula for L of 2t. So I think it would be helpful to recall what L is. L is equal to F star G. And maybe instead of using T, let's use a different letter to avoid confusion. Let's call it S. So L of S would be equal to F star G of S. And that would be equal to F of 2S if S is between 0 and 1/2. And this would be G of 2S minus 1 if S is between 1/2 and 1. So now we have to sort of put all of this into L. Okay, and that's how we're getting the triple product. You see what we're getting? We're getting the formula for this product. It's going to be L, but L first F, then G, and then H. And then we're going to see this is going to agree with the way we have defined this triple product, where it's F, G, and H. So now we have to sort of write these out. L of 2t. So it depends on what this 2t is. So basically, you think of 2t, you think of that as S. Okay, you think of that as S. So L of S is, you double it, right? So L of 2t would be equal to L of, so what would be L of 2t? So S, so that's the S, so it's F of 2S, so you double it, so it would be F of 4t, and this is if t is between 0, so it has to go up to 1/4 now. It goes up to 1/4 because S, so S is 2t, right, 2t, but when you solve for t, you divide by 2, so this goes from 0 to 1/4. And then you have the other pieces. So I'm not going to do the other pieces because my goal is just to show you what this is. So basically, this is what you get. When you do F composed G, composed H, you end up getting, so as a function of time, these are the equations that you get. So these are the functions. It starts off F 4t, starts off as F of 4t if t is between 0 and 1/4, and then it's G of something if, and then it's H of something if. So you have to do these computations. There probably is like a more clever way to do it, but then the price to pay is you have to think about being more clever. Sometimes it's better not to be clever and just to do the computations. So that's what this, so this is like a function, right? This is a path, this is some path. So a path is a function of time, and that's the way it goes. It starts off F of 4t like that. Now, what are we claiming? We're claiming that when you calculate this juxtaposition, that's equal to this triple product with these cutoff times. So it's 1/4. It goes 1/4. And if you notice what we're doing, that's exactly what that is. You see, that's exactly 1/4, right? It goes from 0 to A, from 0 to 1/4. It goes from, you see, it goes up to 1/4. You see, this is how the triple product is defined. From when t is between 0 and A, it's f of the affine map. So it's t divided by A. So t divided by 1/4, that's 4t, and that's exactly what we're getting. So it's f of 4t, t goes from 0 to 1/4, and then you have to verify what the other things are. So in the end, this is exactly the same thing as t of 1/4, and the other one is going to be 3/4. So I'm sorry, that's incorrect. The other one is going to be a half. Okay, so you have to check that, unfortunately. But all of these proofs are somewhat messy. They all have to do with like rescaling time from 0 to 1. And when you have a lot of different intervals, there's a lot of mess with those inequalities that one has to work with. Okay, so this kind of concludes, so this justifies this one, and for the homework you can justify the other one. So if we're willing to accept this product is equal to this triple product, and that is equal to that triple product, and the claim says that the triple products, no matter how you cut up the time intervals, are always going to be homotopic to each other. So then that completes the proof that the associative law is the associative law produces paths, but they're going to be homotopic to each other. So it remains for us to justify this claim. So why is this claim correct? Okay, so where does this claim come from? So so that's I think the nicest part of the argument is to justify the claim. So there's some cleverness, there's a lot of clever stuff that's involved in working it out. So let's therefore finish up and justify the claim, and that would complete our lecture. So what we're going to do here is let us define. So construct the following function. So for lack of a better name, let's call it phi. I do not want to call it f because we already used f. We're slowly running out of letters, if you've noticed. So let's call it phi. So this is going to be a function from I into I, okay? And I'm going to draw a picture of this function rather than giving a formula. Actually, that's what Moncrief does. He does not even provide a formula for it. But this is the way the function is going to go. Here's your cutoff intervals. And let's say your cutoff intervals are A prime, B prime, and 1, like that. And the way this function goes is it's basically, so you have these points, and it's just the affine, it's just the affine function that kind of goes like this. Right? That's the affine function. Whatever it is, it's 3 different pieces that you have there. And then one has to observe that, if you do T A prime B prime and you compose with phi, that's T of AB. That's T of AB. So why does this work? So phi, it's the affine function that takes the interval from 0a to 0a prime. It takes the interval AB to the interval A prime B prime, and it takes BA to the interval B prime A. So the idea here is if you take something, you see, like if you just go back to how this is being defined, it's basically if T is between 0 and A, if T is between A and B, and this is if T is between B and 1, right? So those would be like the piecewise conditions for this triple product. Now, notice that if T is between 0 and A, phi maps that to 0 to A prime. And so then when you do this composition, you're going to end up with, you're going to end up with the exact same inequalities because, so again, if T is between 0 and A, when you apply phi to it, it's going to give you something from 0 to A prime. And then that is giving you exactly this, right? So you can maybe do a computation here, but I think you can sort of see it just from the picture. So now, yeah, Moncrief does not even explain why that's the case. He sort of just asserts it. But I mean, hopefully you can understand that. If you cannot understand it, then the one thing that will always work, if you just put in the calculation. So, I mean, maybe we can do this. So let's say that T is between 0 and A. Okay, so let's do it on this interval. When we take T and we put it into TAB, what do we get? This is going to be the first function, right? This is a triple product. It's the first activation function, which is f. And it's going to be t divided by a because we're scaling the time. So if t is between 0 and a, when we evaluate this for that time interval, we get ft over a. Now let's see what we get over here. Phi of t, what is that equal to? What is phi of t? Well, what's the slope over here? The slope, you're doing phi first. What's the slope? You're going up like that across. So it's a prime divided by 8t. So that would be the slope. Now, and then you have to put this into this function. So then you have t a prime b prime evaluated at phi of t, which is a prime over at. But here, because the time is rescaled by a prime, you divide out by a prime. So this would be the first activation function, and then it would be a prime over at, and then you divide it by a prime. And once they cancel away, you can see what you get. You get ft over at over a. So you verified that on this interval, when t is between 0 and a, this function and this function, they agree. And then you sort of check it for the other intervals. So that's the reason for why one has that relationship. Okay, so to continue with this, so here's the clever part. Okay, so this next part is clever. Is very clever. This is not something that you would typically think of. So phi, so this is a map from I to I. So phi is a path. It's a path in the unit interval. You see, that's the part which is really interesting. This entire proof that we're doing, it's all about paths in X. X is our topological space. So kind of we're staying in X. But now we're realizing that because it's a mapping from I into this space, the interval, phi is a path in the interval. And where does it? It starts at 0 and it goes to 1. So it's a path in the unit interval from 0 to 1. And the identity map from I to I is also a path. It's a path in I from 0 to 1, right? The identity function, it starts at 0 and it finishes at 1, so it's also a path. Now recall what we said. Since I, this is a subset of the real line, of course, is convex, the unit interval is convex, all paths are homotopic. Homotopic. So what does that mean? Thus, there is a homotopy. Let's call it capital H because we already use lowercase h, so we really are running out of letters. You should kind of go back to this proof and just see how many letters were actually used. So there is a homotopy that will take us from phi to I. So there's a homotopy. So in a convex space, right? In a convex set, any two paths that begin and end at the same point are automatically homotopic. So there's some homotopy between them. So this is from I times I into I. So that's a lot of I's. But you have to understand, this is S, this is T, and this is your space. So there's 3 different meanings of I. This I is for the interpolation parameter, this is for the time parameter, and this is the space in which the paths are living. You see, these paths are living in I, right? Phi and the identity, you're viewing them as paths in this space. So that's why you have 3 different I's, because they have 3 different roles. But in the end, it's the same, it's the same space, but it's just serving 3 different purposes. So that's why I say that's like the clever part of the proof. So, and what does it do? So H of TS, so what kind of properties does this do? So H of T0, so that gives us the first path, phi of T, right? That's the first path. That's when S is 0. When S is 1, that gives us the identity. So H of T1 is the identity. So the identity is just T. That's the formula for the identity. And then you have the endpoints. The endpoints never move. So H of 0S is 0 because it's a path from 0 to 1. And then you have H of 1S that's equal to 1. So you have a path homotopy. Okay, so now look at this. So the cleverness keeps on going. So you have I cross I into I, and this is H. And then the next thing that we have is we have we have a mapping into X, and we can use this triple product A prime B prime, because do not forget that the triple product is a path. So it is a mapping from the interval into X. Okay, so this is a mapping from the interval into X, right? So this is a mapping from the interval into X. So we have this mapping over here. Now let's take the composition, right? So let's take the composition. So we have this composition where we go H first, and then we do T A prime B prime, and this composition takes us from I cross I into X. And we claim, and now check, this is a homotopy between the path T A B and the path T A prime B prime. So let's check why this is a homotopy between those paths. So let's start evaluating. So this is the time parameter, this is the interpolation parameter. Let's see what happens. So when we do T A prime B prime evaluated at H of T comma 0, what is that? Well, H of T comma 0, that's phi of T. Okay, so that's T A prime B prime phi of T. And if you recall, we kind of talked about that earlier above, right over here. That is equal to this. So that gives us TAB. Okay, so that's the claim. It's a homotopy from this one to this one. Now let's see what happens when S is equal to 1. So that would be T A prime B prime H of T comma 1. So that would be T A prime B prime. But when S is equal to 1, the homotopy was equal to the identity. So that's just equal to T. So in the end, this is just T A prime B prime. So look at that. You've constructed a homotopy from this one to this one. So you just have to check that the endpoints remain fixed throughout the process. So let's check the endpoints. Let's see what happens when you have this is 0 and this is S. Well, HTS, H0S, that's 0. Okay, so that would be T A prime B prime at 0. But the path, it starts at P0. So that's P0, right? This is a path, and the time 0, it starts at P0. So that starts at P0, and then you have the other one, right? And the other one at H1 comma S, that would be T A prime B prime at 1, and the path finishes at P2. So look at that. You have constructed a homotopy. You have created a homotopy that takes you from this triple product to that triple product, and it keeps these points fixed throughout the interpolation process, which is required for a homotopy. So fairly long argument. As you can see, this is not easy, and you can look up at other books, but I think no matter what you do, it is pretty involved. It's not particularly super hard. It's just somewhat tedious to write out the argument. So we'll finish here.